Welcome, everybody, to the February edition of our papers and lightning talks. So we have two papers lined up for today. I'm going to go first, and I'm going to talk about this new image generation paper that garnered quite a bit of discussion. It won one of the two best paper awards at NeurIPS, although I think this last week people are talking a lot more about our second paper. So we'll have Ryan come up next for that. So this paper is VAR, it's visual autoregressive modeling. And I like this paper in particular because people have been taking transformers and sort of copying the success of LLMs and using transformers for lots and lots of other different fields. AlphaFold uses transformers, a billion things use transformers, but for image generation, not for classification, for image generation, the results have been somewhat lukewarm so far. And so this paper tries to do something different. So just to give a quick high-level overview, what the authors do here is they want to generate the power of LLMs. And what people had been doing is in an LLM, you have an input sequence. And so maybe they would try something like a raster scan where you break the image into patches and then you just kind of go across the top from left to right, and then you go to the second row from left to right, and so on. And it works, but there's something kind of unnatural about that because a pixel in the middle of this dead center of the image will depend on the pixels above it, but not at all on the pixels below it, which seems a little bit weird, right? And within the same row, it depends on the pixel to its left, but not at all the pixel on its right. So there's just something about like our natural understanding of images and the relationships between images, between pixels. So there's going to be tight relationships for local pixels that are very close to you in all directions. And then certain general relationships that where like if you have a picture of a dog, then the color of the coat is going to have a certain relationship, even for pixels that are very far away and possibly in any direction. So since that's sort of an unnatural thing, there's been discussion about, well, how can we do something different? And this is a paper that seems to have found a successful recipe. So what VAR does is it says that going from low resolution to high resolution is a natural sequence that has a clear ordering. Okay, just like language, English, we read left to right, has a very clear ordering. This is the clear ordering from low res to high res. And it has this nice property that
Sure.
a medium resolution image will depend on, sorry, one second, guys. Just gonna pull this up one sec so that I can. All right. Hopefully we can kind of manage the audio. So if you say that a medium resolution image depends on a low resolution image, but that whole image, then once again, you've restored this property where it depends on the properties, not just of pixels in a certain direction, but all the possible pixels in that lower resolution image. And so you can imagine, like, if we have a dog just sitting on the grass, maybe a very low resolution image, we can see the color of the coat and it's kind of blocky and we can see the green of the grass and the blue of the sky. That's all we're really getting. But that's good high level information that tells us this is a, let's say it's a German Shepherd, a brown and black something in a green background with a blue sky, right? And then we can, as we get higher and higher resolution, we start to see things. And so then once you're getting close to the final resolution, you may say, there's things I know about, like whatever, the paw, the face, if one eye is a certain color, then almost all the time the other eyes can be the same color, those kinds of details. So this seems like a really nice natural sequence. But as we'll see, like, okay, that as a high level brushstroke, that's fine. But then how do you actually do this? How do you pull this off? So when we go through this, we're going to look at a number of different concepts. These are older concepts that are used in order to build this. So we're going to talk about, again, very briefly for the purpose of just this high level overview. but we're going to use variational autoencoders. And tokenization happens a lot in transformer-based image models. But for things like patch tokenization that VIT uses, it's basically projecting into a continuous space. So you may have a 16 by 16 patch and you project it to a whatever length 128 vector of floats. There's infinitely many possible length 128 encodings because it's just a floating point. So what we really want in order to use our LLM-like transformer for prediction, we need a discrete vocabulary, just like language models may have a vocabulary of 30,000 tokens or 50,000 tokens or something like that. So in addition to regular autoencoder, VAE autoencoder technology, we're also going to use vector quantization. So if you're familiar with VQ-VAE, and technically there's a VQ-GAN addition where they just add an extra loss to make the images look a little better. So we're going to use VQ-VAE. We're going to use a very vanilla LLM. It's basically a clone of GPT-2. And on purpose, and this is one of the things I think that was really strong about this paper, they use GPT-2 mostly, almost completely as is. And so what they said is, we don't want people to say, oh, well, you had really good results because you used some fancy new LLM, you used a better activation function, you used a better this, a better that. They're like, no, we used ancient technology and we still were able to beat these other models. And then what we're going to see is that when you're going from low res to high res images, these images are not going to be just one token anymore. And that's another thing that I love about this paper. I think this is an underexplored area with transformers and LLMs, in that language, we've just been predicting one token at a time. And now what they want to do is they want to predict an entire image. They want to predict multiple tokens at once. How exactly do you do that? Like there's not a super obvious precedent for how you do this. It's not like, it doesn't take like rocket science, but it just requires a little bit something. So we're going to need to figure out how to do that, and we're going to have some special masking to get that right. So that's just a high level overview of the concepts. So let's just go one layer deeper. Okay. So as I talked about, for LLMs, we have this natural ordering to language. Okay. Technically, doesn't matter whether on the paper you do left to right or right to left. We think of language as just this one-dimensional linear sequence, and it has a clear order. And so we model this. This theoretically, you could say, okay, somebody asked me a question, and I'm going to output, 16 tokens. Let me just predict all the 16 tokens at once, and that would be this massive joint probability problem. And so what we do is we decompose it, where we say we're just going to have the next token be conditional on all the tokens that we've seen so far. Before I ever saw this work, might scratch my head and say, is that really enough? Is that really just that little conditional probability, one token at a time? Is that sufficient? Turns out that GPT-4 works pretty well, right? So to copy that, you can see here a simple, a smaller example where there's a picture of a parrot, and we've just broken it up into 9 patches, and you kind of go top row, left to right, middle row, bottom row, like that. So as I said, this is a little bit unintuitive because, for example, patch 5 depends on patch 4 and patch 2 that are right next to it, but it does not depend on patch 6 and 8 that are also right next to it. Okay. This also has a problem that if you have a relatively big image and you have relatively small patches, you end up with a lot of patches. And when you have a lot of patches, 2 things happen. One, it takes a lot of transformer inference steps in order to output all of these patches. The other thing is, as your sequence gets long, as people know, with this quadratic cost, then the cost of doing all of this goes up. So really just trying to figure out how to do this, and it hasn't worked really well in papers and models so far. So what do we do instead? So we're going to have this, as I said in the overview, we're going to have this spectrum from low res to high res images. Okay. And it's best at this point of the game if you just think of images as an image. Don't worry about what's the data representation. At this high level, it's fairly intuitive that like, oh yeah, I can see, again, we have our parrot that like, maybe this third one over here, you're starting to see some of the pattern. And so if I asked you, is the parrot facing to the right or is the parrot facing to the left? You probably could look at this thing that's labeled R3 and say, yeah, I'm going to guess that's facing to my right because the beak's black and I can see there are these black pixels over here on the right, right? And then definitely R4, you're starting to really, if I asked you, what is that? You can say it's a parrot, but there's going to be fine details about the feathers and other things that still haven't been resolved. And as I was saying, there could be some global dependencies where, you know, part of the parrot that's blue, maybe that I think that's maybe the wing, you know, has general global dependencies on other parts of the wing that are also blue. And so by having this high res image informed by this lower res image, you can sort of communicate information up. So in one sense, I feel like you can do parallels to like diffusion, where the image sort of slowly comes together. Uh, the vanilla idea of diffusion, it's a little bit more like you have noise, you have these weird pixels, but you're sort of getting the gist of it. This is actually different in the sense that you literally have something that's blockier, chunkier. There's not necessarily noise with individual little pixels, but rather there's just noise at this scale level. Okay. So hopefully, I'll pause here. Any questions just in terms of this idea of we've found ourselves a one-dimensional natural ordering, and it seems to have the right inductive biases for images in terms of how we can say the conditional probability of a higher resolution image on all of its priors, all the smaller images, kind of makes sense.
I have a question.
Yeah.
So what is the ultimate function of having this autoregressive process at the end of the day?
Yeah. So the question is, what is the purpose of having this autoregressive process? So with language, we've seen that at least what I thought might not be a strong enough prior, a strong enough conditional probability, is actually able to generate amazingly complex sentences and solve word problems and do things, even though it's a really kind of a weak conditional relationship, right? So the idea is if you have the right conditional relationship with images, maybe you can solve really complex image problems. And in particular, I think that one of the ideas is that you build something and it kind of works and you're like, yay. And then you start scaling it up and you make it bigger and bigger and bigger. And ultimately, what we see in a lot of models, there's a slide at the end that has the curves, that the performance just gets better and then it just hits a wall. Your performance just doesn't continue to get any better. The superpower of the transformer GPT architecture is that it continues to scale as you get bigger and bigger. So when we talk about those power law scaling laws, okay, recent with the advances in computing power, people have gone back and built giant versions of older architectures. And so it turns out that like you can actually get an LSTM model that's just as good as GPT-2. Which at the time we would at GPT-2 we wouldn't have thought you could do that, but now we have enough compute and whatever, we can just crank away and we can actually build it. But the thing is, if you just keep making that LSTM bigger and bigger, it'll plateau. So the same thing happened with Mamba. 1 year ago, Mamba came out and we're like, wow, at like the 1 billion size, it's like just as good as an LLM. I haven't seen specific results, but I'm just sort of inferring from the absence of anybody building, Mamba-based GPT-4 that it doesn't work. People tried scaling it up and ultimately it plateaus. So if you have any kind of inefficiency in your architecture, in your sort of prior to prediction conditional probability, you're going to hit a glass ceiling. Okay. And so the idea is that maybe if this is a very true, no inefficiency, no garbage, no missing stuff, so like the truth, the whole truth, nothing but the truth, right? If it's got that kind of relationship, then we will actually see these scaling laws, and that if you power it up, then given a hard enough image problem, all you need to do is grow your data and grow your model size. Those are not necessarily trivial, but nevertheless, you won't hit a wall.
So this is a means to overcome that plateau.
Yes, yes. So right now we have things, and yes, also this might be a little faster and this might be a little whatever, but that's the main thing, is that you want an architecture. And so ultimately, if you get all of these things, maybe you can then work on being sample efficient in training, and you can work on being fast in generation. But ultimately, you want something that sort of learns well to begin with.
We're just kind of following up on that. Can you clarify a little bit of what you mean is what would you consider as inefficiencies from that architecture?
So what are inefficiencies? So for example, for raster scan, this idea that a pixel a patch cannot depend on a patch below it. You could imagine I could come up with a intentional counterexample where all the information you need is below the pixel, and then you're going to make a really terrible prediction at that pixel because you just haven't seen the thing that you needed yet, right? Yeah, maybe that only comes up X% of the time in images, but fundamentally, that's the phenomenon that at a local and a global scale, you're not collecting all the priors you could be in the right way.
One question. So you mentioned VQ-VAEs. So is it here that the similarities are, obviously you also mentioned the concept of we're going to have like a vector space and it's going to be quantized and we're only going to use the vocabulary to represent the Latin space at the end. So do we also do like the similarities with VQ-VAE is that we start with the denominated space and then we build up decoding back into the image and then that's loss function?
So the questions about VQ-VAE and the latent space, let me actually get to that in the next couple of slides. So that's the perfect question to lead to. Yeah.
Not really precedent for looking at the pixel below, etc. In voxel, so like ray tracing for voxel, there's some people ray planing where you basically say, hey, let's create a sphere or a box of radius r. This is the same color. There's nothing changing for that distance. So that's something that may be applicable to this.
Yeah. So I'm not going to be able to reproduce your comment in full, but in terms of like ray tracing, I'm not a computer graphics person. I don't know everything. The issue though is that if I said I've trained this model on ImageNet and it knows cats and dogs and things, generate a picture of a dog. Okay, you can't draw a box around a pixel to inform it because you don't have any of the pixels below it yet. You just have a blank slate. You only have the pixels above you and on your row to your left. So you can conceptually say, yes, just be informed by everything around you, but I only have half of the things around me. That's the fundamental problem. And so it's a chicken and the egg problem because you're like, well, then just generate the pixels below you. Well, how do I generate the pixels below me? Because they don't have the ones below them yet. And there have been people who said like, oh, instead of doing raster order, we'll do a spiral, we'll do a space filling curve. But it's always the case that when you have a sequential ordering, there are pixels that you should be informed by that don't exist yet. And this idea of going low res to high res, you don't have that problem. You still have to decide, is low res to high res a good idea? But every pixel in resolution 4 has access to every pixel in resolution 3. The model still needs to learn how much to weigh the local versus the global dependencies. You shouldn't say this pixel on the dog's paw is highly dependent on the sky, So you need to learn those patterns, but at least you have the ability to have all the data that you want to depend on at your disposal and obviously logically ignore the things that you want to ignore. All right, so let's keep going for a second here. Sorry, actually there was a question in the chat. Yeah, so So I'm gonna explain a little bit more. So hopefully that'll answer the first question. And then yeah, you can come up with different orderings, but you still have this fundamental problem that some pixels don't exist yet. And that's what we're trying to find a better, I'll call it a better inductive bias. So the thing is, how are we going to implement this idea of going from low to high res images? I said for now, to start with, let's just ignore the idea of how do we represent. But now, okay, now that we've done that and talked about, is this a good inductive bias? Now let's actually get down into it. And it's kind of hard. I mean, when you get to the later resolutions, you're talking about a whole lot of pixels. And are we going to somehow jam that into one token for our LLM? That doesn't really seem right. So we're going to want to do a couple things. And one of the things we're going to need to do is we're going to need to reduce the dimensionality. We cannot work in pixel space, okay? This is a pretty common thing, even like diffusion, you know, the move from pixel-based diffusion to latent diffusion. So we'll talk a little bit about autoencoders here. And again, this is just going to skim the surface so you can do further reading. But a regular simple autoencoder, you know, you can imagine you just have some fully connected layers. Gradually, they get smaller and smaller, and you reach a bottleneck in the middle that is your compressed embedding. And so this is a very common technique in order to get embeddings, but this is a deterministic process. So if I say, here's a sample image of Lassie, okay, and I get this embedding Z, and I say, okay, now go generate me some images. All I'm going to do is get Lassie over and over and over and over again. There's no way to get Lassie in a different pose. There's no way to get another collie. You just get this one thing. So we need something that's not deterministic. And for that, that's where the variational autoencoder comes in. So instead of having just a fixed bottleneck, we're now going to have a probability distribution that it compresses it to. And so here you can see it expressed as a multi-dimensional Gaussian. So you have a vector length of means and a vector of standard deviations. And I think this is just a diagonal covariance. So there's just a vector instead of a square matrix of standard deviations. Regardless of the details of training and whatnot, the idea, though, is that I now give it an input, which is a picture of Lassie, and it says, I have this probability distribution centered around what I think this concept is that you're trying to teach me. Now, from that probability distribution, I can sample, and I can generate many different images. If I give it the right input, the right direction, then I can say, okay, look, here's Lassie running, here's Lassie sitting, here's Lassie sleeping, here's, you know, whatever. Okay. And then obviously we can get more and more complex in terms of, you know, make it text conditional or whatever. So variational autoencoders were some of the early image generators. Not going to talk about them too much, but for this paper, we are going to use that concept, but we're going to add another layer to it. And so that's going to be vector quantization. Sometimes when I talk to people about vector quantization, they ask, is this like some very fancy concept? And in my mind, the best way to explain it is it is not. It is just a way of taking your idea of rounding and expanding it to vectors of whatever length. So if I had floating point numbers between 0 and 1, and I said round it to the nearest 100th, you would have 100 buckets. And you would just simply say, for each number, I'm going to assign it to whichever bucket is the closest. There's other ways you can think about rounding, but that's sort of my distance intuition of how you assign floating point numbers to one of these 100 buckets. I'll throw in that you don't have to have 100 uniformly spaced buckets. You could actually have the buckets that are, say, denser around 0.5 and sparser around 0 and 1 if you wanted to, okay? You could learn what are the right 100 buckets that get you the best coverage of your floating point numbers. Let's say they're not uniform random, okay, right? They're distributed some other way. So you could learn that. And then ideally what you would want is roughly the same number of numbers to fall into each of these 100 buckets. So if you just say, fine, I did that. Now how do I do that on a length 8 vector? It's really logically the same process. It's just that your 100 buckets are going to be spread out in 8-dimensional space instead of just linearly. So it's a little harder to draw them, but you just start with 100 buckets and you assign every vector to its closest one. And if you want, you can train them so that the buckets themselves are not uniformly spread out, but rather they get clumped based on where your data is, so that you have roughly the same number of vectors that get assigned to each bucket. So that's my way of saying that I don't think I think it's possible to think of vector quantization as really just multidimensional rounding with learned buckets. It doesn't have to be some really complex concept. So what we can do is in our VAE before, we had this Gaussian distribution shown in the diagram. So now what we're going to do is instead, we're just going to have buckets that we assign things to. And the common terminology for the list of buckets is our code book. All right, one sec. There's a question. Let me just check this. All right. So you got it. So the code book is going to become the vocabulary for our LLM. And in this case, when you build a VAE, you pick the code book size in advance. You pick how many buckets you're going to have, which is pretty much what we do with our LLMs, is we pick, am I going to have a 30,000 vocabulary, 50,000, 100,000? And so this is the way in which we will now take our embedding and we will discretize it so that we could use our familiar GPT-2 architecture in order to do predictions. All right, so this is just a little side comment on dimensionality reduction and discretization. So then we still have to kind of finalize, how do I take an image and shove it into, have different scales and shove it into here, okay? So the top bullet, VQ-VAE, it'll embed an image, but we're not quite all the way there, okay? So the solution that they came up with in this paper is we're going to break the image into patches, but we're going to give low-res images fewer patches, and we're going to give high-res images more patches, okay? And it's probably easier if I just explain exactly how it did it rather than the theoretical concept, okay? So basically what they do is they take the image, they run it through CNN, and they get a 16 by 16 and I don't know what the other dimension was, but 16 by 16 by some number of channels representation at the CNN bottleneck, okay? And when they want the super low res one, what they literally do is they just call the PyTorch, the linear algebra interpolate function, and they shrink it down to a 1 by 1, which basically means they just get the average of all 256 pixels. And so they say, this one average, I'm going to run through the vector quantizer, and that's the sole representation of the entire image. Next higher is going to be a 2 by 2. So I'm just going to call like the PyTorch equivalent of CV2 resize and say, here's my 16 by 16, resize it to 2 by 2. And then I'll run each of those 4 into my vector quantizer. And then for the next higher resolution, I do 33. So we do 1, 2, 3, 4, 5, 6, 8, 10, 13, 16, or whatever. And the final one is the full 16 by 16. So that one gets 256 patches to fully represent the image. By the way, these were ImageNet images. So this was trained on a relatively small problem. This is not trained on super high res. So these are, I believe, 256 by 256 color images for whatever, 1,000 classes for ImageNet.
Can I ask a very quick question?
So
what you described as the ground truth while training, it's like what you showed before, it goes from small to big and then it gets the whole image. What you just described, is it like the ground truth, or is it like how you train back the entire, like, I just don't get what it is exactly.
Yeah, so the question is like, what's the ground truth and stuff? And I haven't really explained that. What I'm saying though is that our different resolutions, how we will represent them as data, is that the lowest resolution is going to get one single vector, which will be represented by our VQ-VAE single codebook number. So literally, if our codebook is, I don't remember what the size is, but let's just say it's size 16,000, then the lowest resolution is going to be an integer between 1 and 16,000 that just represents the bucket that was the closest to our shrunken representation. And then the 2 by 2 is just going to be 4 integers, and so on and so forth. How we train this and everything, I haven't said yet, but that's what the actual representation means. So one of the questions is each resolution going to have their own code book? Intuitively, you might want different code books, but and I've seen other people talking about this paper and asking that same question. It's a really good question. However, the purpose, where we're headed, we haven't talked about it yet, but where we're headed is that we want our transformer to take resolution 2 and predict resolution 3, the next slightly higher resolution, okay? And we would then want it to take resolution 3 and predict resolution 4, and so on and so forth. What that means is that every resolution must have the same vocabulary. That's the way LLMs work. You can't change vocabulary halfway through your text where somebody asks a question and they say, what is the tallest mountain? And then you just change your vocabulary. No, it has to be one vocabulary over all time. So what we're going to do is we're going to say each patch is using a shared vocabulary, but low res gets 1 patch. Next res gets 4 patches. Next gets 9. Next gets 16, and so on and so forth until the final one gets 256 patches, and it can therefore have a lot more information content packed into it. We're still going to have a decoder that interprets those patches. So we're not saying that these patches are literally just pixel values, okay? The embedding into these patches can be anything that the model wants to do, but we're just capping the amount of information that's available to each individual resolution. Question, Tony?
Yeah, so you mentioned resolution, and the question of resolution. So we're just wondering, are either of these factors the reason why Stable Diffusion, for example, a lot of the libraries can train to generate at 512 by 512 and work fairly well, but if you change it to 512 by 768, you get a lot more fingers, for example.
So the question was about Stable Diffusion and changing from 512 to 512 to 512 by 768. Honestly, I don't know the answer to that. We can have a conversation about how the diffusion models work, but I'm not really sure about that. Okay, so second bullet here, we're going to need a special VQ-VAE. We can't just use a vanilla one. We need a special one that's going to understand different resolutions. And what we just talked about is that the decoder is going to be able to make good sense of the high res images as well as make sense of the low res images. So then finally we get to the LLM part, okay? So our LLM, it's supposed to predict the next higher resolution given actually not just the previous one, but all the previous ones. So if you're trying to predict resolution 5, you have access to resolution 1 and 2 and 3 and 4, okay? So as I mentioned in the preview, GPT-2 predicts 1 token at a time. So the input always grows 1 token at a time. If you've ever seen one of those autoregressive mask diagrams, you see it kind of looks like a triangle. It's just got kind of a straight diagonal. Pet peeve, I actually hate the way people make those mask diagrams because for whatever reason, people never label the axes and say which is the query and which is the keys, or even the fact that you're supposed to know that queries and keys are the 2 axes, but they never say which is which, and they never say which is the lower end and which is the higher end. And you're just supposed to magically know this. So for a bunch of data scientists, we've in those diagrams, we've really violated the first 3 rules of how to make a chart. So, but nevertheless, if you've seen one of those, ours is no longer going to just be this nice triangle. It's going to have these chunks because we're going to have 1, and it's going to be what the 4 pixels that you're predicting all get to look at. And then when you're predicting 9 pixels, they don't get to look at each other, but they get to look at the 4 and the 1. And then when you're predicting 16 pixels, the last of this, because ultimately we'd still have to write them out sequentially, okay? but we're going to create a mask so that the 16th pixel doesn't get to see any of the 15 that came before it. It's only going to get to look at the 9, the 4, and the 1. Okay, so we're going to have a funky looking mask, and then that basically will let us sort of reuse GPT-2 as is, but predict in chunks where again, there's no extra information that later pixels at a certain resolution have an advantage over the earlier pixels you output. Yeah, so it seems like a sliding window, but in this case, the way we're sliding the window is we're sliding it not uniformly, but we'll slide it 4, then we'll slide it 9, then we'll slide it 16, then we'll slide. That's a nice analogy. Okay, so ultimately what is built is this multi-scale VQ-VAE, and as was mentioned, all the scales embeddings, they're using the same code book. It's just you get more patches for the higher level ones. I believe from the paper they said they tried this where they just built, the 1x1, the 2x2, the 3x3, the 4x4. Ultimately, what worked better is they said the 2x2 is not the full image, but rather the delta of the full image minus the 1x1's information. Okay, so if you take the 1x1 and you just spread it out, and then you subtract that. And so if you're familiar with like Whisper, many of these other audio models, they all use residual vector quantization, where they vector quantize and then they subtract that from the raw audio signal. And then from that delta that's remaining, they vector quantize. And then when they have that, they subtract that. And then and usually it's like about 4 times that you do vector quantization. And in that case, I think it's because like the amplitude of high frequency and low frequency signals in audio is different. And so I think early vector quantization tends to get low frequency data, and then later ones tend to get high. And maybe there's something similar in images or not or whatever. But essentially that's what's happening is instead of just saying we have these different resolutions that are copies of each other, as it were, each successive higher resolution is just representing the delta of whatever the previous resolutions missed. And so when you want to reconstruct the image, you actually sum up all of your resolutions, and then you send that to the decoder based on that. So I'm obviously skipping some of the details, but I'm just going to keep going here. So not going to go through here, but if you look at the algorithm that's in the paper, basically what you're going to see is they're going to say for 1 to k, in this case, k was 10, okay? Like I said, they start 1, 2, 3, 4, 5, 6, and then they skip some numbers and they get up to 16 by 16. But you're going to start with your 1x1, and then later on, when you build your 2x2, you have to already have had the 1x1 because you're subtracting that from your raw image. And then you subtract the 2x2 from that result, and you keep subtracting and subtracting. And so if you think about like XGBoost or something like that, this is sort of a similar operation where you just keep trying to refine on whatever you missed in your earlier steps. So the training is you train the multi-scale VQ-VAE to be able to reconstruct images. So it's how does it quantize? How does the encoder, I think, is a frozen CNN, so that part's not trained. But the decoder, I think, does need to be learned. But anyway, you train this, and then this guy is frozen. So when you actually start doing your transformer training, your GPT-2 model, this part is not learning. This part is already fixed. It's just saying, here's my best shot at how to compress images and whatnot. And so then you can see here, I don't think this is a great diagram, but down here we have the blockwise causal mask. It has this sliding window that we talked about. And as usual in papers, neither of the axes are labeled. But so what we're simply going to say is I'm going to give you the 1x1, predict me the 2x2. I'm going to give you the 1x1 and the 2x2, predict me the 3x3. I'm going to give you those 3, now predict the 4x4. And that training basically works just the same way as GPT-2. You just have an error based on every next token prediction. It's just that now we're predicting tokens in batches instead of one at a time. So there's only 10 inference steps to go from nothing to the full 16 by 16, which gets sent to the decoder. Okay. And this is in contrast to, it would be 256 inference steps if you did the raster scan thing. So then when you want to generate an image, so anytime you use these architectures like VAE, you throw away the encoder once you're done. It was useful for you, but it's not used for generation. So they did ImageNet. You give it what the class you want. I want a dog. Okay. And from that, it predicts the 1 by 1. It's one token. And then it predicts the 4 by 4. And it keeps repeating 10 times until it predicts the 16 by 16. You're iteratively summing these as you go. And so your grand total sum of all 10 of these predictions then gets sent to the decoder, and it spits out your pixels. And now you have your 256 by 256 ImageNet image. So that's the process. The results here basically are really, really good. And if you look at the paper, you can see the details, but not only do they have really good scores for image quality, but then also on the right, they say, if the amount of time it takes our big model to output an image is normalized to just 1, then how many times faster or slower? So you can see this model took 168 times longer to output an image, and it was worse. So yeah, yes, we have state-of-the-art results. Every paper has state-of-the-art results. But in this case, I think that they don't seem so cherry-picked. We can probably believe. We had a conversation about scaling and whatnot. So there's some things in here. I'm not going to go into the details, but at least up to the size that they built, which is not that big yet, the model seems to scale well, and it seems to follow this power law. So the hope is that it doesn't hit a glass ceiling. And so on this chart, you can see, for example, the DIT model, it got bigger. So it worked really well when they made it bigger from size 1 to size 2. And it worked really well when they went to size 3. And then they made it bigger, size 4 and 5, and it just didn't really help. That's the phenomenon that we hope to avoid when we have the right inductive bias that's not adding or subtracting anything from the core, data problem in and of itself. All right, so here's some sample images, and if you look in the paper, you can see that they show within each block, it's left to right earlier in the training before the model was very good. You get some really lousy images and weird artifacts, and then it gets better. And then also as you scale up into the bigger models, you get better and better. And so clearly this bottom right image is got a lot more detail and whatnot, and at least, the right number of fingers, the right number of necks, that sort of a thing. All right, so I'm going to wrap things up here and try and save time for the R1 discussion for everything else. But it's fast, generates high quality images. Hopefully we have the right inductive bias. Code's available. You can play around with this. And there's already another paper, an Infinity paper, where they did text conditional. So you can actually say, I want whatever, an astronaut riding a horse, and it'll generate that for you. They also have some other things. I haven't deep read the Infinity paper. So I think this is interesting, and I like the fact that, again, that they didn't just try and copy an LLM, that they broke some rules. And one of the big ones is predicting multiple tokens at once. I think the idea that you can apply more information density to some things than others is an idea that, in my opinion, is going to pan out. Certain recent papers like the Meta, whatever it was called, byte, whatever encoding paper, my understanding of the thesis of that is that not all words, not all tokens have the same amount of information content. And so they let this byte encoder kind of decide, when do I have a mouthful and I'm going to actually send that to the LLM. I think the simplest way to think about it is we use a form of byte pair encoding in order to create our vocabulary. Byte pair encoding was invented for compression, for signal transmission. And so the whole idea of byte pair encoding is that we have shorter signal representations for really common words like the, and we have really long, expensive representations for words that get used super rarely, whatever, supercalifragilisticexpialidocious, right? And we took that technology and each takes the exact amount of space in an LLM because they each get exactly one token that is the same dimensionality. So maybe we can find a way to be more efficient. Maybe it's like the byte paper, but maybe we can actually say, oh, you're doing some math here, or you're doing some medical thing, and I'm going to somehow give you more information density here. But when you say the the tall guy, like maybe you just don't need as many bytes and tokens in order to represent that information. And that might then allow the LLM to focus its computation energy where it really needs to and not really spend theoretically as much energy processing the as some other word. Final note, the paper I did find to be a little bit hard to read because of all the notation. So I do have actually in the appendix just a little cheat sheet here for if you want to go through, like an image is a three-dimensional object that has pixel values, height, width, channel, 3 channels, and all the values are I don't know if they are, but typically they're like floating point numbers between 0 and 1. And then you can see that like as it goes through the embedding, it becomes a 16 by 16, and then it goes through the code book, and then these become integers based on the code book size and so on. So if that helps anybody who wants to read more about the paper, this isn't going to explain everything, but it is just a little bit of a cheat sheet for all the different notation that they have in the paper. Yeah.
Is it too far-fetched to say something like basically that the conclusion from this paper in a way is that the understanding the fundamentals of LLM can basically help us have the same performance level without necessarily having all the bells and whistles, because in this case they're kind of connecting it with GPT-2, and so basically demonstrating that thinking deeper on the fundamentals of how LLMs will operate can also help us, or is that far-fetched to say?
Yeah. I think in terms of the fundamentals of LLM, we have this conditional probability where you say the next word depends on all the previous words that you've said. And it would appear just by experimental demonstration that that's enough. That like you can imagine, and this would be even more true in another language like German, where you have concepts in your head and you're just holding them and you're waiting, and then they come at the end of the sentence, right? So you sort of need like a stack or whatever that you're like maintaining as you're spitting out words. LLMs don't have a stack. They literally just say, here are all the words that I've already seen. I think in English, this works better. There's not that many times when you know a word you want to say, but you just have to stick a bunch of other words in there first, But like I said, I think in German, there's times when, what is it? Like the verb comes and the noun comes way at the end of the sentence or something like that, right? So you know that you want the subject to be the boy, but you just say blah, 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 the boy at the very end, right? But anyway, so yes. So the idea is, if we're going to extend the power of these LLM architectures, really the stackable transformer architecture, then let's find out what the right conditional probability that we should be basing it on. All right, cool. All right, I tried to go fast, Ryan, but probably still never go that fast.
It would be interesting if they could implement FFT transformation of an image and then go take a low resolution frequencies and then add high frequencies and create a dictionary of an image like that.
Yeah. I was actually thinking some kind of like Fourier transform or whatever of the image and doing that, doing low res to high frequency explicitly, just basically, which is I think what you do with audio with RVQ. So maybe that's another way of saying this is a natural, intuitive, inductive bias. We start with low frequency, or imagine like you do PCA and you just have like low rank approximation and you work your way up to high frequency, high rank approximation. So I think there's lots of other experiments, but hopefully this helps people head down that road. I'm not aware of anything done with optical illusions. I'm sure there probably is something, but I'm just not personally aware. Ryan, turn it over to you.
All right. So I will be talking about DeepSeek-R1. So this is taken the internet by storm. Everyone's been freaking out about this. NVIDIA lost a whole bunch of value based on the release of this model in this paper. So it's been super talked about on Twitter and LinkedIn and everywhere. I'll start by just actually showing the interface. So this is very similar to ChatGPT. So people have fallen in love with ChatGPT and Sonnet and all of these other models. You ask it a question, it gives you something intelligent back. So this is DeepSeek. This is just kind of a Chinese equivalent. This is a company that has put all of this effort into building a competitor model to OpenAI. And they have this new model R1 that has been very, very popular. And they've also open sourced it. They've released the weights. They've released a paper on it with a lot of great detail. So people have been digging very deeply into this and learning all of the ins and outs of it. So just to show what it can do, I ask it this question: can you explain to me GRPO, which is one of the techniques within this model? And it's kind of funny because it shows me its thought process. So all of this is like its own internal thought. And it's funny because it gets this completely wrong. It doesn't know about itself yet. So GRPO, it thinks stands for some other concept entirely in procurement instead of machine learning. And so I can go, hey, you're actually wrong. It gives me this response back. No, I meant this specific thing. And then it thinks for a little bit and it goes, oh, I was wrong. How do I correct this? What do I have to think about in order to? And it still actually doesn't know what GRPO is, but it kind of reasons about it and thinks, okay, well, it's probably this other thing instead. So interestingly, DeepSeek doesn't know about its own GRPO, but if I go over to ChatGPT, I ask it about PPO, and then I ask it to compare it to GRPO, it knows about it, it does a search, it figures all of this out, and so it can compare the two. So just kind of interesting point. Everyone's been happy about DeepSeek, but I take the two and compare them, and ChatGPT is still giving me a better.
I think that DeepSeek isn't doing the regular update.
Not yet.
Yeah.
Yeah.
Quick question, are you running on the 6 billion or the 70 billion? Were you running on a service or as a local model?
Service. Yeah.
This is the online service, yeah. And so one thing to note here is this has the thinking on, which is the R1 model, and it also has access to search. So if it wanted to, it could have gone online and said, look this up, but it just chose to take a stab at it without. In difference, the GPT-4o ended up making searches for it and checking out what GRPO was. So this isn't actually what these models are meant for. The reasoning is not for figuring out the definitions of this, but it's just kind of interesting that ChatGPT chose this, whereas the DeepSeek tried to just make a guess at it. But I just wanted to start with that just to show here's what it is, and then we'll talk about the details of how did they actually build this? Why is everyone interested in this? So the focus of this R1, their big goal was to improve the reasoning of large language models. So OpenAI has released their O1 and they just released O3 Mini yesterday. So that's an even stronger model that they've released. And so a lot of these large language models have gotten good at answering questions and doing various things, but in a lot of problems, you actually need to extend this to thinking through the problem. Like if you have a complicated math question, it can't just get it on the first shot. It has to work down factorizing something or working through the steps of a problem. And so that people have been trying to figure out how do we make the models learn this process rather than just trying to guess directly on the answer. And so one of the properties that they want out of this model is for it to think in English or Chinese or some consistent language so that you can just read it and say, okay, it's following a chain of thought that makes sense. We'll see in some of their initial work, it's outputting all of these thinking tokens, but it was just incoherent. As multiple different languages mixed together, it's a sequence of numbers. It's very difficult for people to look at and troubleshoot and say, okay, its thought process was correct, but its final output was actually incorrect. And so the goal is to make this behavior emerge without generating a whole bunch of data just via humans. So in theory, you could take a whole bunch of math experts and say, solve all of these problems and give all of your steps of work. And then you have this massive training set for the model to learn from. The big idea here is if you just have the question and the answers, can you teach the model the in-between to figure out, okay, I need to think in this way. I need to factorize. I need to add these two numbers together. I need to do all of these pieces in sequence in order to get the correct process without just going input, output in a single step. So this training process is split into different phases and will mostly be focused on the post-training phase of this. So the pre-training phase, DeepSeek released this model V3 base, which is their third version of an LLM. And this was all focused on just pre-training against the internet. So guess the next token, guess the next token. Here's 10 billion tokens, 10 trillion tokens from the internet, just learn about the world. And so that's that pre-training phase. And then the post-training phase is saying basically learn how to follow instructions, learn how to do reasoning, all of these different additional things. Give it a personality, have some customization. So when you ask it, what model are you? I'm DeepSeek-R1, all of that stuff gets added in post-training versus the pre-training, which is just saying, train against the internet, all of the text that we can find. So there's lots of different ways that you can do post-training, and this one will specifically be interested in the supervised fine-tuning and GRPO, which is the question that I was just asking DeepSeek and ChatGPT about. So focusing in on GRPO, imagine you have this grid layout, you have a car, and you say, I want to go over here. This process gets split into a bunch of discrete steps. So you might say, I go up, I go right, I go left, or I go up, I go right, I go right, I go up, and then you get to your goal, and at the end you get a reward. So you get a +1 or something like that. But there's actually many different ways that you could take this path here and get to the same outcome. And so that's kind of one of the big problems with reinforcement learning. The thing that we're trying to solve for is we have some final goal, but we don't know all of the intermediate steps. What's the optimal way to do this thing? And so reinforcement learning is trying to solve this problem when we have sparse rewards. We don't know the correct step for every single piece. So this is a very simple example where we have this grid world where you can just go up, left, right, down. But in our scenario with the large language models, they have a vocabulary that's size 64,000 or something like that. So it's much more complicated than just up, down, left, right. And the number of valid ways that you can answer a question is massive. You can start with a different word and have an entirely different sequence, and it can still actually be the correct answer. So one of the common ways of solving these kinds of problems is with PPO, and I won't go into the full details of that, but in that scenario, you typically have a policy, which is a model that is deciding which actions to take next, and you have another model that is typically the same architecture, but is trying to do something to figure out how good the different states are. So it really, if you're in one of these corner states, it really wants you to go right, for example. And so if there's other things here, you say, okay, I really don't want you to run into a wall. And so that's kind of the function of the value network is looking at those and deriving what's a good state to be in. And so the difference between PPO and GRPO is that GRPO sacrifices that value network in place of just doing more sampling of the policy network. So the value network is telling you how good all of these individual spaces are. But the GRPO, what it's actually doing is it's saying, okay, make many different samplings of this output and then compare them to each other. Which ones are getting good results, which ones are getting bad results, and try and push it towards the better results and away from the bad results. So if you said, okay, run this car simulation 64 times and some of them reached the end and some of them didn't, then you say, okay, do more of the good ones, do less of the bad ones, and give credit to all of the steps in between that reach the good scenario. And so one of the big problems in reinforcement learning is credit assignment. So we have this sparse signal where you say, we got to the end goal, we didn't get to the end goal, but all of the intermediate steps to get there, it doesn't necessarily tell us a whole lot about whether the process was correct or incorrect.
Can I ask a question?
Yeah.
So in essence, GRPO is the methodology that uses a more exploratory way to get to the right answer by trial and error. And then PPO would be a policy, a model that GRPO uses in order to optimize the process to get to the right answer, or it's a methodology differently in itself?
It's a little bit different in the way that it derives its reward. So how it defines what's good and what's bad. So in the PPO, it has the value network that is telling you at each individual step what's good and what's bad. Versus in GRPO, it's saying compare against more generations. So the reason that they chose GRPO over PPO is introducing an entire extra model to define what's good and what's bad. And when you're doing this with a 671 billion parameter model, having a second copy of it that you're training in parallel is very difficult to do. So they said, if we just do one copy of it and we just do more generations, that's actually easier than having a second copy that we also train at the same time.
And the question is that, like the way they train it is to ultimately determine if coding problem, for example, works or not. So instead of like having to judge every step, it judges the outcome of this entire thing, and then it becomes much more complicated.
Yeah, exactly. I'll talk about that a little bit more in later slides. Go ahead. Yeah.
Just a quick comment. I think many people may know, but DeepSeek is a Chinese startup. And so because the US laws prevent selling the latest generation of GPUs to China, there's incredible pressure when they're doing research to try to require less memory and fewer GPUs. So cutting the number of GPUs needed in half just by switching from PPO to GRPO, if the algorithm works, is like a massive leap thing. And other innovations they did also cut the amount of GPU they needed in half. So you combine a few of those things and suddenly you need a tenth as many GPUs. And so that's hugely
A tenth of the GPUs for training.
They also made optimizations that allow them to use fewer GPUs during inference. Certain optimizations worked for training, some for inference, a few of them for both.
And what did it do to the inference required to, did it, like if you compared it to long three, did it cut it down?
So that would probably get a little bit more into some of the optimizations of the base model, DeepSeek-R1 that Ryan mentioned. But basically, there are a number of optimizations they do that dramatically reduce the inference cost as well. So
The compression, the context compression.
yeah, so ultimately that's why not only were they able to train with a lot less GPU resources, but right now their cost per token for inference is a lot lower than like Anthropic or OpenAI.
Oh, really? Very good point. Well, two other points in that. We don't know how much meta LLM that everyone actually spends. But what DeepSeek claims it took them 2 months on, I think it was 2,000 H800 cards. The other main programming aspect of it was they used PTX rather than CUDA. So it's a little bit closer to assembly on the GPU as opposed to running it through a C type of thing.
Oh, that's different, because I thought they had to go down like the right part to the um, but, so did, if I wanted to host Llama 3, in AWS or Azure, it would be about at least 15 grand a month, maybe 20. And so I'm only looking at this from a tactical perspective. Like, can I host the larger token version of DeepSeek for like 7 grand? Because if I can do that, it now starts to cost justify moving off of OpenAI and others.
It depends on performance needs. If you use older cars, you get them much cheaper in the old rate in the States. It costs a tenth of what a current video card would be. We can discuss that after. Sorry, we don't want to.
Yeah. The bottom line is for similar performance, your costs will definitely be lower. Whether or not what price point you're looking for, we can go into more details, but yes, for the same performance, it will definitely cost less for anyone.
There's a bunch of tweets and people implementing it really low grade hardware. And, so there's a lot of information.
Yeah, and I mean, this is a research model. There will be other iterations, like Ryan mentioned, the original R1s was not really designed to do tools very well, so it doesn't really know how to use like, a Python, and it doesn't even do internet searches very well. So it just wasn't, there's always pressure to publish. So I mean, there's going to be the next version and the next version. Sorry.
Yeah. So on this slide, I have the formula for GRPO, and it's very complicated, multiple steps. And so I thought that I would start with just a tweet that's just explaining it in simpler terms than the formula, and then I'll go back to the formula and kind of walk through what the different pieces are. So this tweet is basically saying how GRPO works. And so the process that it goes through is it generates a whole bunch of answers, and then they measure the score of that group of answers. So the way that they can do this is they focus on problems where they can easily verify it. So like it was mentioned before with code, if you have code, if it executed correctly and got the outcome that you wanted. If it was math, what the final solution is. And so you can easily just verify that. And then all of the in-between steps, you're not really grading. You're just saying, was the final solution correct or not? And so what you're doing is you're measuring the score of all of these answers. Let's say you do 64 of them, and then you compare the individual scores against the scores of the group, and then you want to push towards the answers that were correct. And so a lot of this is stemming on these base models are so smart now that if you kind of sample them and do it multiple times, 3 out of 64 might be correct. And then you're saying, okay, do more of that 3 and less of the other from the 64. And then you can push it to the point where it's getting the correct answer more and more of the time. People have figured out that if you do many generations and then you kind of merge them all together, you can get good results. But if you can do it in a single sequence generation, that's a lot better than saying I have to do 64 and then do some merging of them every single time. So that's one of the innovations there. So this is kind of walking through an example of what that might look like. So at the first step, you have this query saying, what is 2 plus 3? And then the LLM generates a whole bunch of answers. In this case, they're only doing 3. So the first generation is 5. The next generation is 6. The next generation is 2 plus 3 equals 5. And then measuring the score of that, they can look at it and they can say, okay, 5, it got the answer correct, but it gave no reasoning. It just output the answer directly. So it gets 1 point. 6 is incorrect, so that gets 0 points. And then here's 2 plus 3 equals 5. That gets 2 points because it got the answer correct and it gave some reasoning. And so what you would want to do is push towards this number 3 answer. And so you're looking at the average score from the group. So you're doing 1 plus 0 plus 2 from all of these scores up here. And then what you're doing is you want to compare each of these individually to the average. So this answer of 5 gets 0 because that was just the average outcome. It wasn't exceptional in any way. 6 gets a -1. You don't want it to do that because it's doing the totally wrong thing. And then 1 the final generation gets a 1 because that was the above average result. So you're saying push towards this one that gave reasoning and was correct. And so you typically do this with larger groups. You might do 64 or larger and say across this whole batch, which are the good ones, and push towards that and push away from the bad ones. So this is kind of just a simplification of this formula over here. And I'll go back over here and kind of just pick at these pieces a little bit. So one of the things that wasn't mentioned in this is that we're trying to keep the model's initial knowledge. Whenever we're doing this training process, we're probably losing something from pre-training. And so this first piece over here is the KL divergence. And so this is comparing the new model against the original model before any training was done. And it's saying basically, don't move the model too far because you'll start learning your understanding of English and all of the basics. You don't want your model to just completely drift. You want it to stay towards the probability distribution of the original model. Otherwise, it will break and start just hacking towards the individual data that you have. Another piece over here, so this clipping portion is saying basically between all of your steps, you only want to make small iterative motions in the correct direction. You want to cap it in some way. And so what this is saying is basically compare the new model against the old model and then make sure that that's within 1 minus epsilon and 1 plus epsilon. So this is some small factor, and you're saying, okay, make sure that the update is not above or below a certain magnitude. And this A1 over here is the computed average. So this, in that tweet we were looking at, was saying, here's the score of an individual outcome and subtract the mean of all of the generations from that group and divide by the standard deviation. And so this is saying, what's the advantage of that individual prediction? And so this is the part that is comparing the new model against the old model and the advantage. And so this is basically saying for that whole group, take the average of this. So it's many, many terms and pieces, but really it's 3 parts. It's the KL divergence saying stay close to the original model. It's this part saying clip and make sure the model doesn't move too far from the old model. And then this is saying like how good were the individual steps that it took.
One of the questions here, parameters are the entirety of the LLM.
Yes.
7 billion parameters.
Yeah.
Okay.
Yeah. Yeah, so it's the whole model here that's being trained. Yeah. So here's part of their setup. This is the prompt that they use. So this is what they started with, and they're basically saying, we're going to give you a conversation, think within these brackets, and when you give an answer, put it inside of this answer tag. And that's all that they gave it. And then they said, work through this GRPO. And the hope was, okay, expand everything inside of this thinking tag and just use tokens in order to reason about what the question is asking you. And so, like I mentioned before, the reward of the model is defined by rules and automatic verifiers. So for math problems, they know what the correct answer is. For code, they know what the expected output is. And so they give it rewards for getting the correct answers, and then also giving it reward for putting things inside of the thinking tag correctly and the answer tag correctly, just to kind of constrain it to follow those directions. So here's a chart of the results. So this is just showing as they're doing training steps, it starts from very, very poor accuracy. So this is R10. As they're doing more and more GRPO steps, it's getting better, better, better. And so this green line here is O1, and they're also taking consensus. So they do 64 generations of the model, and then they're saying find the most common answer. And so if you do 64 of them versus one, you get this boost of accuracy here. And they find that you get similar behavior out of R1 0. So it gets better, better, better. And then at the same time, they're measuring how well it does when it does 64 generations, and then find the consensus out of those generations. So one of the interesting things that they found from this was that as they were training, the length of the responses got longer and longer. So initially that thinking token region was relatively short. And as it trained for more steps, it realized, oh, I can use this as scratchpad and think through the problem and go through and backtrack and reflect and self-verify and see, okay, I did get the correct answer. And so now you see in R1 and O1 and all of those, you see it thinks a whole bunch and it does a whole bunch of lines of text, and it kind of has an internal dialogue to do all of this processing. And so this is a form of test time scaling, but it's just learned automatically. It realizes, oh, if I do more tokens, I get the answer correctly more often.
If I just jump in, I think this is probably the biggest innovation in the R1 paper, is that think how long it would take you to train people to write really good chain of thought reasoning, how I got from A to B to get my answer, and then pay them to generate 600,000 of those, including very long ones for harder problems. So the fact that they were able to find a way to, in this case, incentivize, but they were a way to get the model to do chain of thought. They never actually told it what chain of thought is, or told it that chain of thought was good, or rewarded it for chain of thought. It's the fact that chain of thought increased it getting the math problems answers correctly, meant that it just got more rewards, and so it saw, I'll just keep doing this and I'll do more of it. So I think that this, it does two things. One is it really verifies that chain of thought naturally helps our GPT style LLMs the way they are now. Maybe there'll be some future LLM that doesn't need chain of thought, but current ones do. And they automated this, so then, you know, without paying billions of people, they could just generate almost as much as they wanted.
Yeah, yeah. So one of the examples that they gave that they thought was interesting was it has this aha moment in the middle of its training. It's doing this math problem and it's thinking through the steps and it's failing, and it goes, wait, I got it. Aha. And then it goes back and it says, okay, here, do these steps actually. And then it gets the correct answer. And so this is an example of it using that thinking tag in order to kind of use scratch space and work through the different possibilities and find the answer for itself. Because I think one of the common things that I do with like ChatGPT is I have it do processing and then I say, no, that's wrong. And it goes back and it tries again and it might get the result on the second try. This is kind of internally doing it itself. It's like, okay, measure if it's correct, verify that I'm doing the steps correctly, and then it can just think for a while instead of me needing to intervene and say, no, you did this wrong, or you did this math error. It's just doing it by itself automatically. So they built this model and they called it R1 0. And so this was great. It had that good property of it's getting better and better and better. But they inspected the thinking tokens and they realized like actually there's a lot of language mixing in here. And when humans go through and read it, it's problematic. We can't kind of verify exactly what it's doing. It's just kind of strange outputs. And so what they did is they said, okay, it's generated a lot of things now, and some of it is valid, some of it is invalid. Just remove all of the invalid ones and use that as a sort of cold start in order to make it follow this pattern. And so what they did is they said, now we have R1 0, and this has kind of started the process. Remove all of the ones that are bad and train from that to start, and then do the reinforcement learning process. And now it's already started with a valid thinking process in place, and they've removed all of the bad ones where it's mixing languages and got other problems in its thought process. So now they do another loop of this and they get the final R1. And so they cold started it and then they did the reinforcement learning process again, the GRPO, and now they have this final model that they can compare against Claude and GPT-4o, and this is their base model, and this is O1 mini, and this is full O1. And so this is the part that everyone's very interested in is now they've recreated what OpenAI was doing and they were charging $200 a month for, and now it's just freely available. Everyone can use it. They can even download the model and host it if they want. And so in a lot of these things, it actually doesn't have much impact on the score, but in certain ones, it has a huge impact. So like if you compare it in code forces, it goes from their base model had 1,134, and it goes all the way up to 2029. So it's fighting against this full fat O1 now. So in some of these tasks, it's really not meaningful, but in other ones, it is a huge game changer because it's specifically in those tasks like code and math, where it got virtually no accuracy before and it's significant leap after that. So like this other math one here jumped from 39.2 to 79.8. That's much better than you would get from saying just scale the model 10 times bigger. There's a certain point where this extra process that they've added is really boosting the performance of the model.
Quick question.
Yeah.
So let me do this right. So in essence, if we were to pinpoint the innovation that we talked about, the innovation of the efficiency of its thought process, and the training is because of the thought sequence that was purified after getting rid of the nonsensical thought processes. And those themselves come as a result of the, what's it called? The GRPO architecture methodology that you talked about. So is that how?
Not necessarily. So they actually showed that that cleanup process didn't truly improve performance, but it made it so that they could inspect the traces and understand what was going on. Because before it was like, okay, I can talk in Chinese and German and English all at once, and it's just mixing all these things together. And then at the end it says, okay, I got the right answer. But when they cleaned it up and said, only do English, then they can actually look back at it. But that isn't the part that got the performance. The part that got the performance was the reinforcement learning to get there and the multiple loops of it. So they do it again and they realize, okay, we can do better with this.
Yeah.
Yeah.
Just briefly, I think in the R10 model, a lot of the stuff they removed was valid. It wasn't incorrect. It wasn't bad. It's just not friendly to humans to have one sentence in English and then the next sentence in Chinese. So, it's like my understanding, little kids in bilingual homes will just mix words in the middle of sentences, stuff like that. And as you get older, their brains haven't changed. They just learn like, oh, you probably prefer it if I stick with one language when I talk to you. And so they just stop doing that. But it's not that it was wrong when they just dropped in a word from English. It's the right word.
Contextually to that.
Yeah. And so if you think about it, if you're solving a math problem, does it really matter whether you say it was a square, it was a triangle in Chinese or English, right? Okay. So I think it's actually kind of cool. I think it's actually neat that if it's trying to solve math, it doesn't care whether it says square or the Chinese version of square. But yes, it would be kind of annoying as a user if you didn't see Chinese, just see all these flaws.
It got negative press because it felt like it was like like a Chinese spyware or something that was coming out.
I totally get like
press
you don't want to release this to the public, but it wasn't. It's not like it was logically broken, and that's what they had to remove.
It's almost like if it's learning context was the thing that led you to have this reasoning process, and kind of like a kid that had the right environment to go through the reasoning process that's displaying. So right now, that's an adult.
The other thing I'll say is that they didn't instruct tune it to do, user and response, user response. It's just in the prompt where it says you're going to kind of have this stuff, right? It turns out that whatever their cold start was pretty small, like a few thousand or whatever. And so it's like, oh, that's a scale that we should actually ask some people to write those. And it's a lot easier to demonstrate what a back and forth conversation looks like than to design a reward for it. So I think actually it's very efficient to say, let me give you the basics of what back and forth conversation looks like, what it looks like to have only English or only Chinese and not go back and forth. And then reinforcement learning can do all the reasoning stuff without having to, having that really good base. So if it required 500,000 to teach it what a back and forth conversation, you would use a different technique. But if you're like, only a tiny number of examples is good enough for it to learn that, then why not just go ahead?
Yeah, but
Reading the table, the only place where DeepSeek kind of suffers is on the simple QA English. Has anybody dug into that? I'm sure they're curious, because that's the only place where you see over a 10% drop.
What do you mean by QA?
So on the simple QA under the English portion, that row, you see 47%, or 47, I assume it's percent, on the OpenAI model versus 30 on the DeepSeek column. Comparing all of those rows, DeepSeek is like within a couple whatever units, but in that category specifically, it's down by 17, which is a lot.
Yeah, but what does simple QA English mean? Like I ask a question, I get one answer. Is that what that means?
That's
I
a
don't-
particular data set, I think.
That's a data
Oh,
Yeah.
it's a data set.
Yeah, it's a
Yeah.
collection of questions and answers.
Because I've tested DeepSeek that's hosted like you did a ton sweet. And it outperforms GPT-01 in every test I've ever done.
American comedy. Where the cable guy
Is
here?
it simple QA from Wikipedia?
simple QA is from OpenAI themselves. So
Oh.
I think that's one of the, yeah.
Never mind.
That's one of that's one of the benchmarks that they've created. So I would put a little caveat on that where they probably also have their own internal data that they've trained against that boosts it in that
So I have a
criteria.
DeepSeek set that I take every LLM through and it releases. And I'm testing both performance and I test both like how it handles edge cases, how comprehensive it is, what I think the boundaries are. And all of them have failed. Those the boundary tests, all of them. But DeepSeek, like by far, performed the most impressively head to head. So that's when I started paying attention. Like, oh wait, the stock market probably should drop. Like something. What do you mean by that? Like I give it complicated tasks that maybe aren't well documented on the internet. To see like how it reasons through those tests and I give it like imagination tests, like imagine the scenario, what should I account for? And then I see like, how it thinks through what it should account for in this imaginative problem. And then I compare it to what I would like after I thought about it. I think very slow by the way. Like the LLMs always think that's my ranking, right? But I compare those results and say, and then I kind of give it like my own like opinionated grade on it. Right?
What's also interesting is that it jumps from 01 uni to 01 from 7 to 47%. Like it's a very big jump unseen anywhere, and 7 is very low. So to me, I think there's like they already said, there's some like leakage that they pass through the training to just get higher numbers because something feels wrong there.
Well, just as a practical matter, because I run everything at home, I like to use cloud stuff. So DeepSeek 70B was the first 70B model that could pass my basic test of blah, 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 bunch of constraints. Here's a single prompt, you give me what I want. Quen would come close, but when I tried to prompt it to correct it for certain things that it omitted, it would inevitably bail out, run out of context, fall into Chinese. But DeepSeek was able to pass the first one. It immediately failed my second test, which was essentially taking the first test, applying that to a plane, and then rotating a plane as opposed to the object and do some things. And as a boundary constraints, I say, don't use 3JS, don't use Babylon, don't use Canvas, don't use third-party frameworks. Using only plain HTML, CSS, and JavaScript, give me blah, 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 blah. And I do it that way because I can look at it and instantly verify if it's correct or not. Llama and Ematron, those would inevitably have rotations of the wrong axes out of the object. The faces would be collapsed on each other, those types of things.
What do you mean? They said it's very good on this stuff. I don't know if that's
Yeah. Well, if it came out this week, maybe, but I can't run that one at home.
No, you can't. No,
then it's used.
But I really like the chain of thought interface. I really, really like it. And I think most people who are testing it really like it because it trains the user what's happening, right? What prompts better and to iterate better.
Opportunity has now been printing the thoughts as yesterday.
Who is?
As a reaction. OpenAI, opportunity.
Oh, they are.
The new
They just
For a
I didn't know
lot,
that.
for a lot of LLMs, you could have turned on chain of thought reasoning parameters if you're running it in full or long or that stuff too. But most people don't like that because it takes a lot longer to give you the answer back. If the difference is between an answer that's wrong and an answer that's almost as wrong but you explained, and the answer is correct and slower, it depends on what your use case is.
I didn't find that true with DeepSeek, but I felt like chain of thought was pretty quick when it was coming back to me. I never felt like I had to wait.
It's very good.
That's part of the value of the DeepSeek, though, is that it's so much faster at generation. It's doing multi-token prediction. It's doing all of the stuff that Ted was talking about. Like that's the advantage, is it's so much faster. It's got that's the paper before this is the V3 base. That has a lot of innovations that we're not even talking about here, and that's why it can generate so much faster. It's that size of model, but it's able to generate much quicker than 405B, for example, from Llama.
I have a small question. So the way it's being trained at the RL portion is that it's only being asked one question by the user and answering the question, and then it's being fine-tuned. Sorry, it's being like trained that way. And a lot of the real life use cases is not only just a one-time question, it's more like of a like just multi-turn questions or conversations. So I'm just wondering if like this puts it into like it's difficult to basically interact with it more than once because it doesn't really take into consideration the previous turns in the training process. Because for example, in the instruction fine-tuning, it's always multi-turn, so it can back and replicates the real world. So I'm just wondering if this is a problem when it comes to the actual inference in the real world.
I'm not sure about that. They didn't specifically mention that, but I did see, like, even in the example I was showing, I did interact with it multiple times and it seemed fine. I don't know exactly how it handles that. I'm sure it's just reading the previous context as if it was regular text. It's not looking at the thinking as if anything special.
My intuition is when you look at those thinking where it says something and then let's take a different approach and then let me clarify this. Wait, and even just like how do they spell strawberry? S-T-R. It does so much of that it's almost like a multi-turn conversation with itself.
I see.
So my guess would be that it probably isn't going to be phased by having multiple terms.
I see. Okay.
The large model is definitely using the same principles of mixture of experts because it's 37 billion parameters active at a given time within the 670 or whatever the process was. I forget the specifics on that.
Yeah, but I think it's a good point. It does not appear from the paper that they expressly trained it.
Right, yeah, because the prompting, the way it's showed, is just like always one question, answer, verification, and then back propagates.
Yeah. So we're almost done. I'll just cover this and then we can have any discussion we want. So one of the other interesting things that they showed was that this distillation process is very powerful. So now they have this data set that is generated from a very strong model. So they did the R1 and then they made the full R1, and now they have a very good reasoning model and they can have it answer a bunch of questions and it has this full chain of thought along with it. And then they said, basically, now we have this huge data set, just train the smaller models on it directly. Don't even do reinforcement learning, no GRPO, just train it to mimic the bigger model. And they were able to create significantly better models than they could if they tried to do that reinforcement learning process on the small model to start. So here's all of their family of models that they trained. So they trained a Quen 1.5B and they got big boosts on all of these models. So they said, here's a small model, slightly bigger, slightly bigger, slightly bigger. Let's try it on Llama as well. And so they saw, okay, this data set that we've created now is very valuable. It can boost the performance of all of these models very quickly, and you don't have to do any complicated reinforcement learning stuff on top of it. So one of the comparisons that they showed there's this QWQ model from Quen, which is its own reasoning model. And so they said basically, look, we can get basically the same result on their architecture using our process. And so they said, look, we can match it. But if we actually took our much stronger R1 model and do the distillation process with the Quen 32B, we blow it out of the water. We have this much better model. It creates much better chains of thought. We can just train on that directly. And now we have a shrunk model that's very good and is better than you could get from doing the same process on a small model. So that's a kind of interesting phenomenon of we could train a very big model to get something smart, and then we can shrink it down and we'll do better than if we started with just a small model. That's a very valuable thing to do.
Is that why OpenAI is saying, yeah, we think they're using our model to train theirs?
Also, they say a lot of
Ask
things.
it. Your expressions will say that it is ChatGPT.
No, this is because it's very common to see on data set. Like in the internet corpus has very much like a sentence because it's like the first like official LLM that converses well. So it's the whole internet is filled with like this sentence. So just replicating this corpus, but I think they say stuff.
ChatGPT lost its job to
So-
AI.
Yeah,
I haven't
Twitter.
believed much of what Altman has said publicly in the last 6 months, and I just realized like he's burning however many billions a month or a year through things that he's just like, oh, well, I used to really trust him, and then as he has continually been proven wrong, I'm like, I think it's just all bullshit, so.
I think the fact that OpenAI is being closed is like it makes it open from the very beginning. Like
Yeah.
this transition for no reason to just decide to go closed.
Well, they can't put their data out because then they have to admit that they stole everyone else's IP in the first place, and that's what they're accusing.
Yeah, but if you just put the weights out and not clean data out, then I mean you don't really open source your model because you need the data to train it, but at least
It's open source, here's a binary.
yeah, just do something. I mean
Changed my opinion on AI safety too. Altman's wrong about that. If he's wrong about all the other things, he's probably wrong.
that's why they left probably. These people.
Yeah.
That's why it's
That's why Elon's like, you know, money back, right?
everyone left us. All of his big people left. So there's a reason for that.
So getting back to R1, Ryan, if you can go back to the previous slide, I feel like possibly there's two misconceptions that are out there about R1. So one thing is this distillation, they use the word distillation, and I don't know, I'm not the most foremost expert, so I'm not trying to be the grammar police here, but most of the time when people use the word distillation in an ML paper, they're referring to hidden style, teacher, student, you use logits as your soft labels for training the student, and that's not this, okay? So whether or not it's the correct use of the word, I'm not gonna argue that, but don't be mistaken that this is the same distillation that you see in 90% of other papers that talk about distillation. What they did is they created 600,000 examples of chain of thought, and they used regular supervised fine tuning on these small models. So that means that when they took Quen and made it better, no RL was used whatsoever in that training process, not in the original Quen training, nor in what they did. They absolutely did an amazing thing, like I said earlier, with RL in order to be able to generate 600,000 chain of thought examples without needing humans. That's absolutely true, and that's a brilliant contribution. But just don't be mistaken that that RL is what made these models great. So everybody who's downloaded a 32 or smaller model, you know, where they did their training on it, there is no RL in that model that you used. So you got the 32B or 7B or the whatever 1B on your computer that you're running locally and you're playing with it, zero RL. So people should really not say that this is like the RL moment for AI if 90% of you aren't using the full DeepSeek-R1 model and you're just using this thing on your local computer and there's no RL in that whatsoever.
So there's 70 beats as well.
Yeah, only the 671 full model on their, you know, chat.deepseek.com is RL trained. None of these other models have any RL in their training. Absolutely, they have RL in the, whatever you want to call it, the process needed to get the training data. But, so yes, so I just think be careful that what the distillation means and whether that has implications for RL. So RL maybe is going to explode with their success with the zero models, but if you like DeepSeek-R1, yeah, maybe that has nothing to do with RL.
Last question.
Yeah.
So let's say, let's take the example where they're not using our app and we're just having binary samples of them. What basically happens is that you're just doing next token prediction, and then you take what the bigger model is saying to do versus what the smaller model is set to do, and you backpropagate from the loss, right? So how is this? I'm just trying to catch how is this different than doing it like in real time, where the small model generates, the bigger model generates, and then you do RL to fix the weights. So how like how is it different in terms of like the loss?
Well, there's three things you can do. So what I think of as just traditional Hinton style distillation, instead of having right and wrong answers, you are trying to mimic the teacher's answers. So if the next token is supposed to be the word dog, normally you would say the best possible answer is 100% probability dog. That's what the cross-entropy loss was doing.
Yeah.
But if the teacher actually picked dog because it was the most likely word, but it was only 40% likely, and all the other words were just below 5%, then distillation would actually force you to try to only get, it would, if you were at 70, it would actually lower it down to 40 to match the teacher.
Okay, so
So that would be Hinton style distillation. And then there's the question of what Ryan showed was they tried just doing RL on plan, and it didn't actually work as well as doing regular fine tuning, but with just fantastic long examples of chains.
okay, I see. I see.
So at the end of the day, it's probably a feather in the cap for the people who are pro chain of thought, pro test time compute, because no RL was involved, but just giving it really good chain of thought got this model to do much better reasoning in 32B or whatever.
I have a couple links I just want to show very quickly, and then we can wrap up. We can continue talking, but just want to wrap things up in terms of presenting. So I have the link to the paper in the slides if anyone wants to look through that, but there's also several very good talks that if you want to learn more about this, you can dig into here. Here's a YouTube link that is very similar to the talk that I gave, but their own flavor of it. So you might want to watch that if there was anything that was unclear to you. So one of the interesting things is that this GRPO concept is already baked into the Hugging Face reinforcement library, because this actually came from DeepSeek Math, a paper that came out a while ago. So it's already open source. You can go play with it. It's very easy to just say train in this way, and it's just automatically set up to do that for you. So people have already kind of said, okay, using the library, how do we mimic exactly what R1 was doing? And so there's people that have posted code snippets saying like, okay, here's the code. It's only however many few hundred lines, and you can mimic what they did. And people have been able to reproduce these results with smaller models, but they proved like, hey, it actually works even when you use the smaller, weaker models. So Yannick Kilcher also has a good paper on DeepSeek Math, and he goes into all the GRPO stuff. So if you want to learn more about that and also look at the DeepSeek Math stuff, that's all there. And then Nathan Lambert is someone that I see posting on Twitter all the time. He was at Hugging Face, now he's other places, but I would say he's one of the leaders in open source reinforcement learning of language models and post-training stuff. And he has a whole like book website. So if there's anything here that you want more details on, he has good details on many things on this website. And then another thing on Reddit, someone made a little diagram showing here's the whole process. So this is the stuff that I described, but if you want to look at kind of the diagram of how everything flowed and what created what, here's a good diagram of that. And I think that's it. Yep. Yeah.
All right, I think we tried to answer questions in the chat as they came during Ryan's presentation. But if we missed any, let me just give an opportunity for people to ask. And then I'll go back to the room, but just wanted to make sure we didn't accidentally ignore or miss anybody who had questions.
Hey, Ted, a quick question. You talked about distillation. I really couldn't get it when Ryan was saying it. Can you explain in, like what he meant by, so you're saying the 1.5 billion model which downloaded in the local computer is not having any RL, basically. And what happens when we apply distillation? So what's the algorithm there?
Yeah, thanks. So I have a question online. Sorry, guys. So a question online, just asking for clarification about my remark about distillation. So in the paper, they use the word distillation to refer to a process where they use DeepSeek-R1 and the process they used for training the 671 billion parameter model, and they obtain 600,000 really, really good example of chain of thought examples where you ask a question and it does a whole bunch of reasoning, and then it says, end of my thinking, the final answer is blah, 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 and it gets the answer right a lot. So all of these small models that they call distilled models, what they did is they took the model that you can get online, say from Hugging Face, and they just did good old-fashioned supervised fine-tuning where they took the text examples and they just trained it on next token prediction cross entropy loss. There's no RL in that. It's the same fine-tuning, people do all the time. Or if you wanted your own custom one where you just took Llama and you were going to add my company, I work for Toyota and add information about Toyota cars, and engines and service. So it's that technique that was used for all of these smaller models that I feel like perhaps 90% of the people are using. So I just wanted to clarify, not taking anything away from how great these models are. I'm just trying to clarify the process that was used to build these was the original author's processes plus good old-fashioned cross-entropy supervised next token prediction.
Okay.
Does that answer your question?
Yeah. But those distill model, how does the distillation process, like, is it like smaller models? This is like pretty much like the distilled model is like pretty much fine-tuning, right, on your own data or something. Is that what I can call it?
Yeah, so they call them distilled models, but it's really just off-the-shelf Llama, off-the-shelf Quen, and I'm going to give it examples with these really awesome chain of thought examples.
Okay.
And do some regular old fine-tuning on it. That's all they did. There's no RLHF, no GRPO, nothing. It's just, I gave it a bunch of text examples that were really good thought processes, and the models got way better at reasoning.
Okay. I get a point now. So they generated those 600,000 chain of thought reasoning from their own DeepSeek stuff, basically, right?
Yeah.
Okay.
So that process to get those 600,000 examples is very, whatever. Look into all the science and engineering that went into that.
Yeah.
But just be clear that your Quen that you're running on your PC, no RL, no nothing.
Yeah. So the 600,000 chain of thought reasoning examples are using RL, but not the one you actually fine tune. That's more like a transfer learning, or it's more like a fine tuning process.
Yeah. They're not directly using RL, but the model that generated those 600,000 examples had RL in its training pedigree. Yes.
Right. But if they had used RL instead of fine tuning or just supervised SFT, supervised fine tuning, then that would be a different game altogether, right?
Yes, and it actually worked worse than the supervised fine tuning.
Oh, okay, got it.
So that was one of the things that Ryan pointed to. They tried it and it worked worse. So like, again, when there's some people who are saying, oh, they used RL, this is the triumph of RL. I'm saying like, yeah, but it actually on those small models worked worse. So let's not quite go crazy over how important RL was for this model being great. RL was very important for figuring out a way to teach a model to do chain of thought on its own without even telling it what chain of thought was, and to automate that process. Credit should be given, but I'm not sure if RL is the reason why DeepSeek-R1 is so great.
But my other question would be like, we did have RHLF almost in all of the models we have been seeing in LLMs. Like, there is some bit of RL in even the foundational models. So, yeah, if you take the parameters and fine tune, there is no RL. But, if you take the model weights, like if I take the 70 billion llama and just do fine tuning, it's more like a RAG thing, pretty much.
Yeah,
Or, not RAG, you can do fine tuning and create your own thing, but there is RL in the, you're kind of standing on the shoulders of RL for doing that. Yeah.
So I'm not going to repeat your whole comment for the room, but yes, we have had RLHF. I'd say probably the biggest difference is that all the RLHF we've done so far was alignment tuning. It was not to teach models to reason. It was not chain of thought.
Okay.
The goal was this is a better answer. This is a clearer answer. I like it when you use bullets versus if you just have paragraph style. Obviously, don't be toxic, don't be sexist. That's pretty much what we've used RL for so far in that last alignment training.
Okay. So this is not really used for optimization, again, choosing which answer is the better,
Yep.
Okay. Thank you, Ted.
Thanks for the questions, Ravi. Anybody else online? I apologize if we didn't get to all of your questions while we were.
Yeah, I got a question. This is more for Ryan. So when I go to inference these bigger models, the Llama 405B, this DeepSeek, I can't tell if it's like an inference time compute issue that they're limiting either the words or the time. I can't tell if it's the model sometimes. And I just get a whole, the deviations seem to be like number of words much greater using these open source models. Have you found something as far as inferencing that works the best?
So Kevin was trying to ask this question for you, Ron. Did you catch it?
The tail end.
Sorry, Kevin, could you just repeat that a little bit? I tried to get my wimpy speaker so Ryan could hear.
Yeah, what's your favorite inference service, Ryan, to use for the big models?
I think VLM and SVLang are good options that I've seen getting better and better. They're kind of going back and forth with new models and new features, whichever one adopts them faster. They're both good. I don't have a particular favorite. I've used VLM more, but not because I love it, just because that's the one I know.
Could you hear him, Kevin?
Yeah, I've tried a number. I'm using Fireworks and I've tried Together AI, Deep Infra. But sometimes they actually cut the model weights too. Like the precision goes down to like 8 FP instead of like 16. So it's kind of, it seems like there might be a lot of traffic. And I just got a 600-word answer from DeepSeek. And the day before it was like 1,300 word for pretty much the same question. So I wasn't sure like if they do limit compute as far as the number of words or if they try to get out things by a certain time.
Yeah, and definitely what you're going to use for serving is going to be different if you're doing it on your PC versus you have a company and you want to stand up a server. So when you're batching many users, there's different optimizations you can take advantage of. Whereas on a PC, it tends to be just you and it. Faye, you have your hand raised.
You're muted.
Faye, are you able to unmute?
Yes, can you hear me?
Yes.
Oh, that's great. Yes, I have a question. I am working on some microscopic images. So I am using a GRPO for those segmentation images or for generating for those automated images. So what I am working on it is mostly about reducing the overfitting for those images, like mostly about to create for any of those individuals segmented images, make it more generalized and robust tumor segmentation across the different images. And I also use it for the boundaries for the batch-based evaluations, that it could make it to find the best ground truth tumor boundaries and medical standards. It can, like with each batch, GRPO can go to rank the multiple candidate segmentation within the batch, and then reinforcing those that align best with the ground truth tumors, for example, ground truth tumors boundaries and those other standards that we have. So my question is, these are the parts that I am using for those image analysis. Do you think that how it can affect on the handling the uncertainty in the medical images or in macroscopic images based on the what I mentioned? And based on the how it could reinforce the most consistent segmentations across the different views rather than relying on a single prediction.
I don't know if anybody in the room might have more expertise on this than me. What I was saying in the chat, I'll expand on it briefly. So if you read like an intro to RL book, they start with value-based things. So like you're playing chess and you can just say, I'm going to assign a value to every board position. So this position, I've taken all my opponent's pieces and, you know, it's a really strong position, right? Has a very high positive value. And generally speaking, that works, but it's just not extensible to the real world big problems. You can only do small little toy problems with that. And then it struggles with, if I'm doing anything with robotics and I've continuously valued things for what's the angle of the robot arm, how do you have states when it's infinitely many different values, right? So then they go to policy gradient algorithms, and where you basically say, I'm going to do back propagation against the predictions, the probabilities of the different actions, and that has very high variance. It's very noisy, and so that's the reason why actor-critic models like PPO they add back in a value estimate. The value estimate's not necessarily great, so it can't be used alone, but the value can reduce the noise, the variance in your policy gradient method. So that's why I was saying in the chat that if you use GRPO, I don't think this is a silver bullet algorithm that's going to work for every RL problem, because you're basically averaging over your batch. The job of the value network is to average over everything that you've ever seen, that you've ever been trained on. Now, many of them are going to be different, and so it's not applicable to your current situation. But nevertheless, in theory, the value network should be averaging over all batches you've seen up till now, whereas GRPO is only averaging over the current batch. And so I would expect that for generalization and noise reduction, that you're going to pay a price in terms of GPU usage, but that PPO should, in general, do better than GRPO. And I don't know if anybody in the room has anything to add, because I'm not an RL expert.
I'm not an expert on this, but it seems to be that GRPO will work better if there's a situation where there's a known good, essentially a Nash equilibrium position versus getting stuck out of the local in a cubic graph. Local maximum.
Does that help, Faye?
Yes, thank you. So that makes sense that PPO's value estimation, they can help stabilize learning. That is very useful in handling the noisy back propagations.
Yeah,
exactly.
And that's also why you see all this like region proposal, the clipping that's in GRPO, and there's clipping also in PPO, where it's, you know, it's within 1 plus epsilon and 1 minus epsilon of our current. You know, we just don't allow the advantage to create that large of a gradient that we're going to back propagate. So we're gonna cap the amount of change in any one step. basically because we know that we have really noisy inputs. If we thought the inputs were really, really good, we wouldn't clip them. We would say, let's take a big step in the right direction.
Exactly. Because, for example, for the 3D macroscopic images, so since those images data sets, they contain lots of variations. Like, for example, if there are tumors, the tumor sizes and shapes, they have a very lots of variations. Do you think the GRPO, it can provide robustness by, for example, comparing multiple segmentation in a batch rather than relying on an absolute value estimation?
I don't know. Probably I'd have to spend longer talking about your problem and your whole pipeline. But you know, again, just in general, like these RL algorithms, if you have a good reward, they will seek the reward. It's really, really hard to design the perfect reward. What's that principle that says that like if you have a metric for your company, then like any metric can be gained. And so when the
metric becomes the end itself,
when the metric becomes the end itself, it becomes a bad, right? Short's principle or whatever. I don't know. I forget what it's called. But so it's the same thing here. If you say like, all I want you to do is to maximize this thing in a language model, and you don't have the KL loss, you know, in order to constrain it, then you just get reward hacking, and you'll get some pathological examples. So, you know, in sales, you say, okay, I'm going to reward you based on more sales. And so the guy, you know, sells, you know, 5 million deals that either you lose money on or it's worth $5 for you. And you know, any metric can be gained. So
it's still fascinating that principle can also apply to human.
Yeah, because it will just mathematically seek that.
Yeah.
It's not trying to be sneaky, but it just will. And so you know,
It's called good hearts.
good hearts. Thank you.
Nice.
Okay.
Thank you.
Thanks, Faye.